Hi everybody, this is Mr. Gerhard, and we're going through polynomial functions, which is section 3.1 in our pre-calculus book. I'm going to go through this kind of quickly because, again, this is review from Algebra 2. We're going to do some things all kind of lumped into one big long video here. And the other thing is, if you are having difficulty with any of these topics, I suggest that you go back to my polynomial functions Algebra 2 playlist and look through some of those things, because that'll probably help with some of the review. We did the whole, I think there's like 9 videos in there, so you can go back and look at any of those if you have any questions. And we're going to get started here with polynomial functions. So first things first, when we're looking at polynomial functions, we have this nice, interesting, and somewhat confusing statement or formula. And all this is trying to say is that polynomial functions are of the form p of x. You could use f of x or g of x, it doesn't matter. A sub n is the coefficient, and that's of the nth term. A sub n minus 1 is the coefficient, and that's of the n minus 1 term, and so on and so forth. And it starts with n and then goes all the way down to 1 here and 0 here. There's no x here because normally we would say x to the 0, and x to the 0 is 1, so there's no need to really even put it there, so we don't. A couple things that we need to know is that 1, n must be a non-negative integer. Whole numbers is another way to say it, so 0, 1, 2, 3, 4, 5, all the way up to infinity. And all a sub i's, or coefficients, must be real numbers. So we're looking for whole number exponents and real number coefficients. The other thing is graphs are smooth and continuous. If we have something that has a break in it, for example, some of the piecewise functions that we were looking at earlier looked like this and then had an open circle and there was a little jump, that's not continuous, and so that's not a polynomial function. We'll put a big red X through it. Okay, if I drew another one that might have a cusp in it, okay, let's just say that's our graph. This right here is called a cusp, and that means that's not a polynomial function. We also have some functions that have holes in them, and when we have a hole in a function, it goes like this, and then there's a hole, and then it keeps on going. If that hole wasn't there, that would be a polynomial function, but because of the hole, it's not a polynomial function because it's not smooth and continuous. So polynomial functions are really fun to draw. You just draw them nice and smooth and continuous, and they keep going on forever and ever. Now, n is this exponent. It's the largest exponent that we have, and that's called the degree of the polynomial. That's going to tell us some things about how the polynomial behaves. A sub n is the coefficient in front of that x to the n term, and that's called our leading coefficient. And that also will tell us some things about how the polynomial behaves and some interesting things about the graphs. The zeros of a polynomial function are the solutions or roots to the equation f of x equals 0. They're also the x-intercept. So where the graph crosses the x-axis, such as here and here and here, all right, those are our zeros of the polynomial function. And there's 2 rules. One, if the degree of the polynomial is n, we can have at most n real zeros. And in fact, we'll actually find out later that they have exactly n complex zeros. And then a polynomial of degree n has at most n minus 1 turning points. That means if I have an x to the 3rd polynomial, at most I'm going to have 2 turning points. All right, and so that could mean the graph could look like that. Here's 1 turning point, and here's another turning point. Those turning points are our local minimums and maximums, and so that's what we're going to be looking at. As I said earlier, the degree and leading coefficient tells us some things about the n behavior of the polynomial. And this is a little table you should remember from last year in Algebra 2. Basically, we're looking at the degree up here, and we have an odd degree column and an even degree column. And then we have leading coefficients. We have positive on top and negative on the bottom. If it's positive leading coefficient with an odd degree, our graph is going to rise to the right and fall to the left. Sometimes we say f of x goes to positive infinity as x goes to positive infinity. That's other notation that we might use. Or f of x goes to negative infinity as x goes to negative infinity. But basically this is a positive sloped line. If I just looked at the end values, this is going to go up to the right and down to the left. Likewise, even functions or even degrees with positive leading coefficients are going to rise to the left and rise to the right. Those are like parabolas that open up. And if you think about it, like 2x squared, that's a parabola. Degree is 2, leading coefficient is positive 2, and that's going to open both of them up. If we have a negative leading coefficient but an odd degree, doesn't matter what really happens in between, but we know it's going to rise to the left and fall to the right. And likewise, if it has an even degree, it's going to fall to the left and fall to the right with a negative leading coefficient. So you can always refer back to these, but that gives us some idea as to what these graphs are going to look like. And so when I see a graph that looks like this, I can say, okay, well, the degree for this is 3, and the leading coefficient is 1, which is positive. This is odd. And so I know with this graph, it's going to do something where it's going to fall to the left and rise to the right. You can see that based off of this information here, odd and positive. And so when I go back and look at it, I know it's going to rise to the right, fall to the left. What does it do in the middle? Well, the only thing I really know right now is that it crosses the y-axis at 8 because this is our constant term. And so I'm not sure what else happens. I'm going to have to figure out some other things, but it could go like this. Oops. It could go like this, or like this, or even like this. Just straight up and through and then keep going up to the right. So there's a lot of different things it could do. We just don't know yet what else it's going to do. I do know that this is going to be the general shape of falling to the left and rising to the right. Over here we have a degree of 4 and a leading coefficient of 3. And so I know this is even and I know this is positive, so I know it's going to be like a parabola. It's going to rise to the left and rise to the right. What happens in between? I don't know. I could have 3 turning points. I could have 4 zeros, but I don't know. I don't know what's going to happen. So one example could look like this. Another example could look just like this. And another example could even look like this. I don't know, but I do know that all of these rise to the right and to the left and have a couple of turning points, at least one, and we'll talk more about that later. Here's end behavior again. We just talked about this. The degree here is 4, the leading coefficient is 1, so we know that's going to rise to the right and rise to the left. What happens in the middle, we don't really know. If we want to get technical about it, we could say f of x goes to positive infinity as x goes to positive infinity, because as I go to the right, my y values go up. And I could also say that f of x goes to positive infinity as x goes to negative infinity. And this is just notation that we use to describe the end behavior as opposed to rise to the right and rise to the left. When we're talking about zeros of polynomial function, this is kind of important. Actually, it's really, really important. The p is the polynomial, and c is just a real number. That's what we're dealing with. And all 4 of these things are the same, and I'm going to use them interchangeably. Don't tell the math people because they might get mad, but I might call something a 0 or a solution or a factor or an x-intercept. It's all semantics. It's all English, so we don't worry about it. But in reality, we have zeros, solutions, factors, x-intercepts. They all mean about the same thing. We have x-intercepts of graphs. We have x minus c is a factor of the polynomial. X minus c is a solution of the equation. And then we can say c is a 0 of the polynomial. So we have zeros of polynomials, solutions of equations, factors of the polynomial, and x-intercepts of the graph. And that's all very important. Now, how do we figure out what these are? Well, we set f of x equal to 0 and solve. And how do we solve? Well, we solve by factoring. Told you we're going to have to do that again. Grouping. We could look at the graph, or we could also look at the table. And what we're looking to see is where that y value, or f of x, is going to equal 0. So let's do a couple practice problems. Here's p of x equals x squared minus x minus 6. Well, first step, set p of x equal to 0. Move x squared minus x minus 6. How do we factor that? Well, this is pretty easy. We could say x minus 3 and x plus 2. Had a brain fart there for a second. All right, so x minus 3 and x plus 2, that's because x times x is x squared. X times 2 is 2x, negative 3 times x is negative 3x, and the negative 2 and positive 3, or negative 3 and positive 2x give us negative x, and then negative 3 times 2 is negative 6. What do we do when we get to this point? We set those factors equal to 0, so x minus 3 equals 0, or x equals 3, x plus 2 equals 0, or x equals negative 2. These are our zeros. 3 and negative 2. Here, polynomial is already solved for us. It's already factored. And so we just take these factors, x plus 1, x minus 1, and x minus 2, and we set all those equal to 0. I can say x minus 1 equals 0, and say x plus 1 equals 0, and x minus 2 equals 0. And so x equals 1, x equals negative 1, and x equals 2. And there's our zeros. It gets trickier. Here's one where we could see what's common in all terms. Oh, well, there's an x common in all terms, so we take that x out, left with x squared plus 2x minus 8. And you can factor appropriately. We have x, and then x and x. We're looking for two numbers multiply together to give us negative 8 and add together to give us 2. That's going to be positive 4 and negative 2. Here we have this x out front, so we got to say x equals 0. We got to say x plus 4 equals 0, and x minus 2 equals 0. That gives us x equals negative 4 and x equals negative 2. Positive 2, sorry. And so x equals 0, x equals 4, negative 4, and x equals 2. Here's the last one we're going to do. I'm going to pull this up over here and say 0 equals x cubed plus 3x squared minus 4x minus 12. And this I'm going to actually group. So I'm going to group these two and group these two. Common in those first two is x squared, leaving me with x plus 3. Common in the next two is negative 4, leaving me with x plus 3. That's good. There's an x plus 3 in both terms, so I take that out, and I'm left with x squared minus 4. X squared minus 4 can be factored one more time, and so we're going to say x plus 3, x plus 2, and x minus 2. Last thing that I need to do to solve this is set them all equal to 0. X plus 3 equals 0, x plus 2 equals 0, and x minus 2 equals 0. Gives me x equals 2, x equals negative 2, and x equals negative 3. Whoops. And those are my zeros. Now all these zeros would transfer over to x-intercepts, and this is kind of important. These are our factors. This is going to come up later. These are our zeros or solution. So we need to make sure that we're paying attention to that. I'm not going to find the zeros of these, but you factor and do the same thing. Now, sometimes when we factor, we get things that look like this. And these exponents tell us the multiplicity of the zero. For example, this factor tells me that x equals negative 3. And this factor tells me that x equals positive 3. These are the multiplicities. This is an even multiplicity of 2, and this is an even multiplicity of 2. What does that mean? Well, it means if this is negative 3 and that's positive 3, what's going to happen is the graph is going to bounce off the x-axis in both of those points. Now you might say, how did I know it bounced off the top and not off the bottom? Well, if I were to multiply all this out, I would have a degree of 4 and a leading coefficient of 1, which tells me it's going to rise to the right and rise to the left. And if that's the case, it's going to bounce off the tops of this because it's got to go up. And if it's got to go up, then that's where our zeros are. That's what's going to happen. Here, I know x equals negative 3, but it's got an odd multiplicity. So that's going to go through or cross the x-axis at negative 3. Here I know x equals 3. Positive 3, and that's going to bounce. All right, so it's bounce, and this goes through. So let's graph it. There's 3, there's negative 3, and my degree here is 5 with a leading coefficient of 1, and so that's going to go up to the right and down to the left. So if I'm going up to the right, down to the left, it's going through at negative 3 and bouncing at positive 3. My graph's going to look something like that. Now it could have some more bumps and dips in it or turning points, but I know at least it's going through at 3, negative 3, bouncing off the graph or touching the x-axis and turning around at positive 3, and my end behavior still falls into play. So that's what's going to happen when we look at those. Now, these are some things that we need to know when we're graphing. You're usually going to probably use your graphing calculator, but we can use leading coefficient tests to check the graph's end behavior, meaning whether it's going up to the right or falling to the right or up to the left or down to the left. We want to check the x-intercepts. Okay, if there's multiplicities, if the multiplicity is even, it touches the x-axis and turns around. If it's odd, it goes through the x-axis. And if it's greater than 1, if the multiplicity is greater than 1, meaning 2, 3, 4, 5, the graph's going to actually flatten out at that 0. We can always calculate the y-intercept by computing f of 0. And we always want to look for symmetry. If it's origin symmetry or y-axis symmetry, if the graph is even, it's going to be symmetric about the y. If it's odd, it's going to be symmetric about the origin. We know that the number of turning points is going to be 1 less than a degree, and it can be no more. It can be fewer, but it can't be any more. And we can check points on our calculator using our table of values, and we can also use our calculator for finding maximum and mins. And we talked about that before in our review of Chapter 2. So I hope that helped. I know it was kind of long. But if you have questions about it, check out some of the other videos and polynomials, and good luck.